Hello and welcome to my talk towards the ZooKeeper-less Pulsar. My name is David Kjerrumgaard. I'm an Apache Pulsar committer and formerly a principal software engineer at Splunk. I've also worked at several companies as shown here, including Amazon, FedEx, Splunk, Hortonworks, and Zappos. I'm also an author of Pulsar in Action by Manning Press and co-author of Practical Hive by A-Press. I'm happy to report that a Chinese edition of the Pulsar in Action will be available in mid-2023 from Turing Book. So look forward to that. So let's begin by talking about Pulsar's data and metadata paths and the differences between the two. This is the basic reference architecture for a single Pulsar cluster. Client applications outside of the cluster publishing and consuming data from the brokers, and a stateless broker layer with multiple nodes for high availability and failover. Finally, a stateful bookkeeper layer for intermediate and longer-term data storage, and at the bottom, a quorum of 3 ZooKeeper nodes for metadata storage. We are all familiar with the data path within Pulsar. Data is published to the broker by producers and published to multiple bookies in the bookkeeper layer. Consumers can retrieve the data from either the broker cache or from one of the bookies in the ledger's ensemble. But what about the metadata path? An Apache Pulsar cluster needs to store metadata. This has traditionally been the role of the ZooKeeper cluster. It is an additional distributed system that is used to track critical information used by both the broker and bookkeeper layers. When you expand your Pulsar instance to include more than one cluster and want to enable georeplication, yet another ZooKeeper ensemble is used as a configuration store for storing things like individual cluster connection information, such as the data URL, the REST admin URL, security credentials, and various georeplication policies, namespaces, subscriptions, and tenant level permissions. But before we could eliminate ZooKeeper from Apache Pulsar, we first need to understand what role it plays in the overall architecture of the system. The first role it plays is that of Pulsar's metadata store. Pulsar requires a significant amount of metadata to function properly. These metadata can be broken down into 5 distinct categories based on the role that it plays in the system as shown here. First would be pointers to data. This contains individual pieces of information that point to other data in the system and are dereferenced by Pulsar at runtime. Second are all metadata used for service discovery. This comes into play when we're trying to identify what components exist within a Pulsar cluster at any point in time and which role they're currently playing within the system. Third is the broad category of system configuration, which covers a broad range of default policy settings for the Pulsar cluster across, like, are globally applicable to the cluster itself. Fourth is provisioning configuration, which we'll get into in that section in a further section, but it has to relate to how information is distributed across the cluster. And fifth, and not least, is the distributed coordination aspect of it, which is the core functionality of ZooKeeper provides. This handles with maintaining control of tracking who has control of which resources, such as a topic assignment to a broker within a Pulsar cluster. So let's begin by section 1. The first of these categories is the metadata used to track the location of data stored in other parts of the systems, aka pointers to data. There are 2 types of pointers that need to be maintained in Pulsar. The first is known as the managed ledger, which keeps track of the Pulsar topic data itself. The second is the ledger metadata, which tracks the bookkeeper replicas across all the different bookies within the bookkeeper system. The managed ledger is an append-only list of all the bookkeeper ledger IDs that are used to store each of Pulsar's topics' respective data. As you can see here, the topic is spread across multiple ledgers. In this case, ledger ID number 20, another ledger ID 245, and so on. The managed ledger maintains this information in ZooKeeper. Then, when a consumer needs to read data that is not in the broker cache, it first goes to the managed ledger to get this information, to identify which ledger to retrieve from the bookkeeper layer, and it gets this information. That's the first pointer of the equation. Now the managed ledger itself internally is stored as in a hierarchical structure inside ZooKeeper itself, as shown here under the root managed ledgers directory. Then it is further stored by tenant, namespace, and topic, as you would expect. So as the number of topics grows, the size of this data increases accordingly within the Pulsar metadata store. Pulsar also includes a tool known as the Managed Ledger Admin, which allows you to administer this data and make modifications as necessary and track this information. You can also examine and retrieve the metadata using the info internal subcommand of the Pulsar admin topics command here by specifying the topic name to retrieve the information and look at it very closely. Here is a representative example of what the managed ledger data actually looks like. If you were to use that retrieve command, this is what you would see. As I spoke about earlier, really the managed ledger is just an append-only list of ledgers. So as you can see, there's a sequence of ledger IDs, each unique, each containing additional metadata about the number of entries within it, its relative size as far as bytes, and whether it's been offloaded to tiered storage or not. So it knows whether it's on bookkeeper layers or if it's been moved to something like S3. It also contains additional information about the schema, and potentially if it's been compacted as well, their metadata would be stored there. The other pointer to data piece of metadata is called the ledger metadata, and it's used by bookkeeper itself to maintain information about where each individual ledger is stored inside bookkeeper itself. This allows us to route a read request from Pulsar to the correct bookie when a Pulsar client is trying to consume topic data. The managed ledger tells, as we saw previously, the managed ledger tells the client which ledger to read next, while the ledger metadata tells it where to read it from. So as we saw in the previous example, the managed ledger might have said, hey, the next ledger you need to read is ledger ID, or ledger 20 rather, and at that point you would check the ledger metadata to find out which bookies currently are hosting a copy of that, a replica of the ledger number 20. Again, currently this information is stored inside bookkeeper in a hierarchical manner, but this time it is numerically numbered and has no relationship to tenants and namespaces and topics, as that information and that overlay is handled entirely inside the managed ledger. They're strictly numeric at this point. Pulsar also includes a tool known as the bookkeeper shell, which allows you to administer this data, and you can retrieve the metadata using the command shown here by specifying a ledger ID. Now if you were to enter this command, you might see some data that looks something like this. As you can see, it contains a lot of information specific only to this ledger itself: what version it is, the ensemble sizes, the write quorums, add quorums, its open state, length, and so on and so forth. It also lists the different ensembles or bookies that contain this information. As you can see, this ledger has been stored across multiple different bookies and can be accessed by any one of them. The second category of metadata is service discovery metadata. This is used to determine which brokers and bookies are in the cluster and to which broker a topic has been assigned, and so on and so forth. You can retrieve the list of all the brokers' advertised addresses using the command shown here. This is inside the ZooKeeper shell, as you can see, and it is a single directory, load balance brokers. This is a fairly static data set compared to the previous category of pointers to data, which is continuously increasing in size as data is added to a Pulsar cluster. In contrast, this data set will only change if and when brokers are added or removed from the cluster itself. An additional piece of information that is kept in service discovery is Pulsar also needs to store broker assignment metadata, so it knows which broker to route incoming client requests to based on the topic name. This metadata changes whenever the broker performs an automated load balancing operation or if an unload command is issued. As you can see here, this is stored in a hierarchical manner, and there's individual entries on a per namespace basis. So namespaces come first, then the name of the namespace, and the relative bundle ID. So again, this is a fairly small data set, but you can see that it stores real-time data around which broker is serving that information or serving that topic or that particular namespace bundle at any point in time. A third and interesting piece of information kept within the service discovery category is that of the current broker load. So in order to support automated load balancing, Pulsar also needs to maintain broker load information in a central location that is accessible by each broker. As part of the broker rebalancing process, each Pulsar broker stores its information about its current utilization as shown here. Again, you can see this is stored in ZooKeeper and stored by each individual cluster name. It tracks metrics on averages and aggregates rather than individual messages around throughput averages, message rates in and out, and information like that. This information looks similar to what is shown here, is updated rather frequently relative to all the other metadata in Pulsar because there's constantly a new entry being made. Every minute or so, this information is updated so that it can respond to load changes in the system as quickly as possible. Load metrics are also tracked at the more granular level of namespace bundles as shown here. This metadata helps Pulsar's auto balancer know which namespace bundle needs to be split in order to have its load more evenly distributed across the brokers. Again, it is kept in a hierarchical manner, nested eventually under each namespace. So the more namespaces you have, the larger number of entries you're going to have as well. You can see here that the short-term data tracks some additional metrics as well that help you understand this particular namespace bundle's load requirements on its currently assigned broker. The third category of metadata is system configuration metadata, as shown here. This metadata deals with cluster-wide policy information such as broker and bookie isolation groups if you are to configure them, tenant-level resource quotas and policies of that nature, and the default policies for namespaces and tenants, including security policies, schema compatibility, and so forth. Basically any policy you set in the broker config and do not overwrite will be stored here. Again, this is a fairly static data set relative to the other ones, and updates can only be made using the REST API as shown here. So once you start a Pulsar broker instance and bookie instances, this information is stored one time and can only be updated very infrequently. Here's an example of what system policy metadata looks like. As you can see from the command, it is all maintained in the same ZK node, ZooKeeper Z node, and this is a fairly static data set as I mentioned before. So you're getting admin policies of the system-wide variety. This is it. These are defaults, things again like dispatch rates, throttling, things of that nature that are globally applicable if not overridden at either the tenant, namespace, or topic level. Things like schema validation enforcement is one such example. The fourth category of metadata is provisioning configuration metadata. This is where all the namespace and topic level policy information is stored. These policies include all the concerns shown here, such as authorization and data retention policies, schema compatibility issues, things of that nature. Again, this is a fairly static data set as well, and therefore highly cacheable, which improves performance on lookups when new clients connect to a topic and need to retrieve this policy information to check that they're within compliance of these various authorization and schema compatibility policies, for example. Each namespace policy is kept in ZooKeeper and can be retrieved with the following command as shown here. Again, this is on a per namespace basis. So again, this grows in proportion to the size and the number of namespaces within your Pulsar cluster. So again, this is some information you have, your individuals such as the bundles that are assigned to it, replication information, all these different policies are set here on a per namespace basis. It can be broken down further. Similarly, individual topic levels would be nested one level below the namespace. So if you had a different policy for public default my topic, it would be a separate ZooKeeper node as well. So while this is a very static data set, it can grow quite large relative, again, to the number of topics that you have within a cluster, which, as we shall see, creates a resource constraint problem on our current ZooKeeper-based metadata store implementation. Last but not least is the distributed coordination metadata, which is used to maintain locks on various resources within the Pulsar distributed system. Things like which broker is assigned to the current namespace bundle, leader election around the ZooKeeper itself, as well as who's the bookkeeper coordination and metadata, syncing and auto recovery metadata as well. So, what is wrong with using ZooKeeper? It's a well-known and reliable system that is used by 40+ open source projects and is fairly well vetted and proven in industrial use cases. Well, the biggest problem ZooKeeper has is its inability to scale horizontally. Unlike other distributed systems, ZooKeeper's performance actually degrades as you add more nodes to the cluster. This is because each node must communicate with every other node in order to achieve a consensus or quorum on what the value of every individual Z node is. This means that the number of network calls each ZooKeeper node needs to make increases in a non-linear fashion, but actually exponentially. It becomes factorially larger as you add another node. Now each node needs to talk to it, so it's an n times n type scenario. ZooKeeper nodes also suffer a significant performance penalty if they have to read data from disk. This only occurs if the data that they're looking for isn't in their current buffer memory, but ZooKeeper has a term for this known as death. Disk is death to ZooKeeper. Therefore, it is only able to its ability to store data is limited to its physical capacity as far as RAM goes to store that information, and it's limited further by networking exponentially having to talk to one another. So it's not a horizontally scalable system. As a result of some of these limitations, of those design flaws, there are some limitations that ZooKeeper has as it pertains to Pulsar. So roughly the amount of metadata that can be reasonably stored and kept in ZooKeeper is approximately 5 gigabytes. Another problem with ZooKeeper is it is a complex system that is difficult to maintain and tune. And last but not least, ZooKeeper was not designed to run in containerized environments such as Kubernetes, and this can cause significant network issues. It was always designed to be run in a physical environment, and networking things such as sidecars and DNS and software-defined networking can prove challenging when trying to get ZooKeeper to function properly in these networking environments. So removing ZooKeeper would have some significant impacts on Pulsar, right? Removing it would reduce the amount of operational complexity, obviously, from having to run an additional system, therefore simplifying Pulsar from a DevOps perspective. Replacing it with a horizontally scalable metadata store would allow us to increase the volume of metadata that Pulsar can store and access. So again, ZooKeeper imposes a 5 gigabyte cap on the amount of metadata we can store, and as we saw in the previous section, this is a significant impediment to the number of topics. Go back to the way that we store data hierarchically in the managed ledger, in the policy information, in the ledger information, etc. This data set grows and grows, and it becomes an upper bound. With 5 gigs becomes an upper bound on the scalability of Pulsar in general. So from a practical perspective, the ability, if we were to be able to release these limitations, this would translate into support for tens of millions of topics and support for much larger topics as well. So next, I want to talk about the development that has been done thus far. Now, all of these efforts fall under the Pulsar Improvement Proposal number 45, or PIP 45 for short. It is a multi-step plan that has already commenced but is not completed, and we'll talk about next steps at the end of this talk. The goals of this community, the community had for this initiative, are shown here. First and foremost, we did not want to implement this logic, the metadata store, directly in the brokers and make them specialized single points of failure within the broker themselves. We still wanted to have sidecar implementation of the metadata store. We also wanted to avoid going down the path of rewriting these complex distributed coordination algorithms again, such as Paxos or Raft. We wanted to design it to assume the facilities of a cloud-native environment first and foremost, and assume that this metadata store would be designed and should operate within a containerized and/or cloud environment. And last but not least, we should simplify the tuning and operation of this metadata store and design it for automated tuning, from growing from a very small cluster to a very large cluster, without a lot of administrative intervention that's currently required to scale a cluster from a very small to a very large cluster. The first step of the development of PIP 45 was to create a metadata store abstraction that would allow us to plug in alternative technology rather than ZooKeeper for the metadata store. And this would further allow us to remove the ZooKeeper API dependencies and libraries from the build path and make it more transparent. Once we had this interface defined, the following implementations shown here were developed. For backwards compatibility, a ZooKeeper implementation was needed. Obviously, people would still want to continue to run ZooKeeper. We wanted to support their metadata store as it existed today, and so this was the first undertaking that we did. We'd also verified the design by adding this additional level of abstraction without losing any metadata or functionality in the Pulsar cluster itself. Next, an etcd implementation was developed to exploit the cloud-native key value store, etcd itself, that exists in most Kubernetes environments today. It was a very suitable replacement, as you will see, based on its capabilities of key management and storing data. Additionally, 2 scaled down versions were also deployed to speed up unit testing and simplify standalone deployments respectively, making unit tests perform much better and making the standalone deployments simpler to use without requiring an additional ZooKeeper just for a standalone environment. Now, once we looked at the metadata semantics within Pulsar itself, as we were designing the metadata interface, we identified 2 main patterns of accessing the metadata. First were the simple key value access and notifications. Right? These are, again, put values, get values, things like that. The other category was complex coordination of systems, as we shall see here in a bit. But that was it. These are the 2 things that our metadata store has to do. These are the things that ZooKeeper provided for us in the past. These are the capabilities that must exist in any suitable replacement. The metadata store interface defines several methods used for key value access, as shown here. So your basic put, get, delete interfaces. All values are treated as byte arrays, and serialization and interpretation of this data is left up to the consumer itself to decouple it entirely from any sort of class or other schema, implementation of Pulsar leaking through in the design. It is a raw, lowest level storage mechanism. There's also a caching layer for quick access to highly scalable and highly cacheable metadata sets, as we've talked about before. Things like policy information. We want to be able to store that once in a cache. It moves very slowly. That way we don't have to go and get this information back from disk or anywhere else and highly optimize the storage for quick access. Things that are accessed very quickly. The other part of the equation, as we mentioned, was the semantics were more complex coordination. Now that very broad term falls into things like coordination services. And we defined the metadata store interface defined a set of primitives that are used for cluster coordination and various activities as shown here. Again, this high-level API hides all the complexities under the covers that ZooKeeper used to provide for us. Things like acquiring a resource lock, or distributed lock over a single shared resource, leader election, and distributed counters, unique IDs, generating unique IDs across multiple brokers that are consensus based and everyone can agree on the same value. Now let's talk a little bit about how the configuration changes, or about the configuration changes you will need to make to use each of these existing metadata store implementations. Just to clarify, each Pulsar cluster actually has two different metadata stores, as we saw in the beginning of this presentation when we were talking about the metadata paths. There's the internal one within the current local metadata store that contains and stores only cluster-specific configuration and coordination information. Again, brokers that belong to that cluster, policies that are local to that cluster, things of that nature. The other replication or metadata store is one for coordination of geo-replication and things of that nature, storing information across multiple clusters to which you belong and accessing a globally shared metadata store to get information about other clusters in the Pulsar instance, tenants that exist across multiple cluster instances, and other entities that need to be globally consistent. Now, in the past, you would specify a ZooKeeper cluster, and there is no change other than the API change itself. So we've deprecated a property within the broker itself and replaced it with these two as shown here. The metadata store URL would be, if you wanted to continue to use the ZooKeeper implementation, you would simply specify a list of the ZooKeeper nodes, both for your local use as shown here, and then optionally, if you're going to use ZooKeeper globally, you would have to specify a separate list of those global ZooKeeper clusters here. Note that in this example, we're using two different sets of ZooKeeper nodes for local and global, which is the preferred and best practice. So these would have to be, and you can swap these out if you wanted to use etcd locally, but a global ZooKeeper, that is also a supported option. And this is controlled entirely by the configuration properties. When you start the Pulsar cluster, it determines your implementation you want to use based on the protocol you specified in these links. So when it sees a ZK, it knows you want to use the ZooKeeper implementation of the metadata store from the list of our 4 that we currently have available. Now, if you want to use etcd as your metadata store implementation of choice, then these configuration properties would look something like this. Each metadata store URL would be a list of etcd nodes, prefixed by the etcd protocol type, followed by the HTTP endpoint that all the different nodes, etcd nodes in that quorum, can be addressed through. Again, note in this example, we're using two different sets of etcd nodes for local versus global, just to specify that. Last but not least, if you want to fine-tune the configuration of your etcd metadata store, again, this is the local one, then you can use the config path property shown here, metadata store config path, to point to a configuration file locally that contains all the settings you want etcd to use. So here's an example of such a configuration file for the etcd-based metadata store. In this example, we use the file to configure security settings needed for connecting to a TLS secured etcd instance. We can specify we want to use TLS, who the provider is. We would, in an actual implementation, specify a path to a certificate, trust certificate, a key file, a certs file, the certificate authority. All these different required properties can be specified here, and allows you to optionally configure these cases where you want your metadata store to act differently than the defaults. And it provides an opportunity for much more performance and tuning is there. So it is a pointer to get a pointer to change and control your etcd configuration. If you want to use RocksDB as your metadata store implementation of choice, then your configuration properties for your broker configuration would look something like this. Again, your metadata store path is now prefixed with the RocksDB protocol type, followed by a path to where you want the RocksDB data to be stored on disk. If you want to fine-tune the configuration of your RocksDB metadata store, then you can use the config path property shown here to point to a configuration file that contains all the settings you want RocksDB to use. In this slide, it shows a simple example of a configuration file for fine-tuning the RocksDB-based metadata store. In this example, we use the file to specify some performance tuning options, and I definitely refer you to the RocksDB documentation for more information on all the properties available. This is merely a subset of some of the tuning configuration properties that are available to you, and then you have full access, pass-through access to all these properties. So again, if you want to tune your RocksDB implementation in your standalone cluster, then this is the way to do it. And last but not least, just for the sake of completeness, if you want to use an in-memory data store for whatever reason outside of unit testing, you can configure it as shown here. Again, you would change the property to point to use the memory protocol prefix, and they would obviously just keep the information in memory, and that would be the entirety. Again, this is a very specific use case for things like unit testing, not recommended for anything other than those types of very trivial use cases, because you can easily use your metadata. You lose your metadata, your complete broker is gone, your broker and all that different service discovery metadata could potentially be lost. So as I mentioned before, we're not quite done, but let's stop at this point and see across the PIP45 process and the implementation we've done thus far with getting etcd and these other implementations in place, what we have achieved, what are our successes, right? First and foremost, from a practical perspective, as part of this effort, we were able to resolve the cluster instability caused by a lost ZooKeeper session. Previously, this condition required broker restarts in order to resolve, which was disruptive to client applications and something that couldn't be easily detected and automated through Kubernetes or other monitoring systems. It really became a source of pain, and this increases the cluster stability quite a bit. As part of this effort, we were also able to implement batching of metadata in order to achieve higher throughput for both metadata reads and writes. Through this process, we accumulate operations into a queue and use the underlying API we've built into the metadata store for bulk access. Again, ZooKeeper multi-access transactions, or etcd, both supports these. And this is a major improvement in metadata throughput. As you can see from this slide, batching provides almost a 500% increase in write operations compared to a non-batch ZooKeeper write implementation. Obviously, memory has significantly better due to lack of disk, and RocksDB does quite well. Similarly, batching provides almost a 15 times or 15x increase in read operations compared to non-batch ZooKeeper reads. This is a significant throughput performance increase thus far, making Pulsar clusters perform that much better. Now, to configure batching, the following properties have been added to the Pulsar broker configuration file that allow you to further tune the metadata batching as you see fit. As you can see here, you can either enable or disable batching based on if a system supports it or not. As I mentioned in the previous slide, ZooKeeper and etcd do. Things like RocksDB do not. You can control the frequency of the batching or specify the maximum batch size in either bytes or total number of operations either way. For those of you familiar with batching with the Pulsar clients, we follow a very similar pattern. The first of these triggers to occur of the batch considers the batch full, so if 5 milliseconds have passed, no matter what size the batch is, we will send that first. Conversely, if a batch have 1,000 items occur before the milliseconds delay, then we send that batch as well and consider it complete. You can obviously tune these parameters to meet your performance requirements. So what's next? We've gotten thus far, we have implementations, we've proven that we can do Pulsar without ZooKeeper, and that's great. But what's on the future roadmap for the PIP45 ZooKeeper replacement long-term strategy? We have defined the following goals for the next phase of development of the metadata service. With increased scalability, support for larger data sets, and lower latency being just a few of these goals. Again, we want to scale Horizontally, we want to be able to hold much larger sets of data, and therefore increase the and then also decrease the latency and throughput of the system. If we are able to achieve these goals, this will manifest itself as a 10x increase in the number of topics supported within a cluster. Again, our resource constraint is 5 gigs in ZooKeeper itself. If we're able to eliminate such an artificial bottleneck, then that obviously increases the amount of metadata, which is directly proportional to the number of topics and namespaces that we need to support. Because again, that metadata grows linearly as you increase the number of data you write to the topics or the number of policies you add in the namespace bundles, etc. So there's a very close constraint based on that memory retirement. We could even have a very small Pulsar cluster, a very minimal cluster of like 3 nodes and a very simple metadata store, be able to support millions of topics. But the handling of the metadata is the biggest obstacle to these achievements, but it's not the only factor. We're also working on metrics collection, lookups, and the overhead of a single topic and global memory limits as well. Thank you all for attending. Please scan the QR code to learn more about Apache Pulsar. Let's keep in touch. This is my Twitter handle. This is my LinkedIn. This is my GitHub repo. And thank you all for attending my talk.